I'm Cliff Trines, Director of General Public Outreach for the National Groundwater Association. It's my privilege to introduce our presenter, Peter Cartwright, a professional engineer and expert on water treatment, including home water treatment systems. He has had more than 250 clients globally, authored some 200 articles, and presented more than 200 lectures in conferences around the world. During the presentation, feel free to type questions in the question box. At the and then hit send to send that question. Do that at any time during the webinar. At the conclusion of Peter's presentation, he will answer your questions. You have a great opportunity to ask a true expert, so please take advantage of that. And without further delay, I'll turn it over to you, Peter.
Thank you very much, Cliff. The function or the purpose of this webinar is to introduce you to the hazards and treatment technologies associated with lead in our drinking water. Lead in our environment exists basically as a solid. It's a metal. It occurs naturally in our soil, in the ground, and it's probably one of the most poisonous of all of the elements that we would ever encounter. The common sources for lead exposure, which normally is in a solid form at that point, is leaded gasoline that gets into the soil, household dust, lead particles, pottery, toys, traditional cosmetics, and generally the presence of lead in groundwater is extremely small, almost undetectable. You can't smell it, you can't see it, you can't taste it, but the problem with it is extremely small concentrations are very dangerous. Where we would normally expect to encounter it in our water supplies is either lead that's in old galvanized steel pipes, certain brass fittings that prior to just a few years ago, they contained a relatively high concentration of lead in the brass used to help in the production of the fittings, and solder used to connect pipes and joints. Prior to the early 80s, one of the principal components of solder used to connect copper pipe to itself was lead. Because of regulations associated with such things as the production of brass fittings, the production of solder, etc., in the last 30 years or so, the concentration of lead in these materials has gone way down. So that's tended to reduce the exposure of lead to humans in our drinking water. However, one of the big issues that was exacerbated by the Flint, Michigan issue 6 months or a year ago is the fact that many of the pipes that are used to deliver water from the main in the street to the home or from the well to the home used to be made out of solid lead. And they're buried, you can't see them, so they present a real potential hazard. Let me reiterate, no amount of lead is safe, according to the National Institutes of Health. The National Groundwater Association recommends that a water supply going into the house be tested at least once for lead. And particularly if the system, both the pump, the well pump system, as well as the piping leading from that into the residence, was installed before the early 1990s, particularly if there are children, because children represent what's called the immunocompromised segment of our population. they're much more susceptible to contaminants in our water supply than a normal adult. And if there are signs of corrosive water, and we'll get into that in a little more detail later. The two factors that can affect how much lead can leach into drinking water are the length of time water is in contact with lead before being used, such as sitting in a pipe that may have lead in the construction somewhere, and the corrosiveness of water, primarily related to pH, although it's not necessarily limited to the pH of the water. The lower the pH, the more corrosive water is typically. So what is the greatest threat of lead in drinking water for well owners? Galvanized steel pipes, certain brass used in plumbing fittings and fixtures or well components, and solder used to connect pipes and joints. So how can you address lead in your water? First, determine the source of lead. This is extremely important, and as I said, you can't taste it, you can't smell it, you can't see it. It has to be analyzed. And when I say analyze, I'm talking about using a laboratory that is accredited by the state or by the EPA and that specializes in analyzing water, not soil, not air, but water. That's extremely important. If the groundwater entering your home is not the source, then have a water well professional look for any components that exceed the government lead contents. In other words, if it's not naturally in the well water, and usually it isn't, it has to be coming from a component through which the water is flowing or the water is in contact. If the well system is not the lead source, then you have to go inside the house and look for things like old soldered copper connections, something like that, that may contain lead and which is leaching out into the water. The three basic options for addressing these issues are replacing the components, if you can identify which components may contain the lead, make sure they meet the federal lead content standards, treat the drinking water with appropriate treatment technologies, or flush the water that had been sitting in the water system for a long time, such as overnight. I'm not as enthusiastic about that because that's treating the symptom rather than the issue itself. So what treatment technologies can be used to remove lead? The one that I most firmly endorse, because it is so effective on virtually all water contaminants, are the under-sink reverse osmosis units. These do an excellent job, and what they basically will do will remove lead, whether it be in particle form or dissolved as an ion, which is usually the issue. Keep in mind that the acid content of the stomach has a pH of about 3 or 3.5, and so if a particle of lead goes down into the stomach, it's going to dissolve and release the lead ion, which is the dangerous contaminant. Distillers will also work very well at this, as will certain filters that are designed just for the removal of ionic contaminants such as lead and mercury and arsenic. It's extremely important that whatever technology is used, that it be listed particularly by NSF or to meet NSF standards and certified to remove lead. The NSF has certain standards depending upon what the technology is, and it's very critical that the product be used to underscore its performance in this particular activity. As I said earlier, low pH, low naturally occurring water with a low pH could is the most likely to be corrosive. But there are other chemical constituents in water that can make it corrosive. So it's not the only problem or the only condition under which lead could dissolve. One comment, a water softener in the home will not make water more corrosive. All it does is replace the hardness with sodium ion. So it's not going to be more corrosive, but if the water has low pH, if it's got certain other chemicals, constituents in it, it could be corrosive. So in my opinion, the best way to measure for the potential for lead in the house is at the tap, at the drinking water tap. The implication, of course, is when water is below, the pH is below 7, it's acidic. And this is what a laboratory would determine immediately when you take the sample and to be analyzed. The acidic water is extremely corrosive in that it will tend to dissolve, try to dissolve anything under which it comes into contact. And this is what is causing what we call leaching of the solid lead, dissolving it and forming lead ion, which is the dangerous contaminant. You can raise the pH of your water too, just as a safety precaution, either by adding a caustic or more commonly by adding a filter, special pH adjustment or what they call a neutralizing filter that will raise the pH and make the water much less corrosive. Good idea anyway. If your water is below pH of about 7, it's a good idea to adjust it anyway, whether or not you have a lead issue, because it's going to tend to dissolve the copper or other materials under which it will come into contact and cause leaks. Now let me say a little bit about the Flint water issue, because so many people have been exposed to it in the media. It's gotten huge media coverage in the last 6 months or a year, ever since it was identified. And typically, this is what the Detroit city water looked like. It is from a different source, and very often municipalities, when they treat their water, they will add what's called an orthophosphate corrosion inhibitor. What that is a chemical that is added to the drinking water, and this chemical tends to coat the inside of the pipe and really create a layer that is relatively strong in terms of its ability to keep anything from leaching or flowing through the layer and reacting with the pipe. So it basically insulates. It's a chemical insulation of the piping material. It's called a passivation layer. And keep in mind that chlorine, it's probably the most widely used disinfectant in the world. However, because it's a disinfectant, it's an oxidant, and because it's an oxidant, it wants to attack things. So the aggressive nature of the chlorine is mitigated by this orthophosphate corrosion layer. And in Detroit, even in those service lines going from the main to the house that may be lead, the possibility of lead leaching into the water was reduced because of this orthophosphate layer that was added. And this is a chemical that is added relatively continuously. Now, what the authorities did was they decided they wanted to go to a less expensive source of water, so they went to the Flint River. And really the problem with this whole thing is not chemistry. The problem is the authorities themselves. They didn't do their homework. And number one, they didn't add a corrosion inhibitor, and the piping the lead piping that was in the homes, there was in the between the service line and the home, buried under the ground, was, because it had no corrosion inhibitor, the lead was immediately attacked by the both oxygen and the chlorine in the water, chloride ion, which is also very corrosive by itself. And then when they tried to add chlorine to disinfect it, chlorine which is Cl2, this also attacked the pipe, and even with the iron pipe, which was the galvanized iron was the most common material used in the service lines, etc. The chlorine attacked that and dissolved the iron and oxidized it, and that's why you may have seen photographs of samples of this treated water that was red. That wasn't the lead that you were seeing, it was the iron oxide. So in addition to a lead issue, the Flint water, because it was not properly treated, was extremely unappealing in terms of appearance. Iron oxide isn't necessarily a health hazard, but it certainly is an aesthetic issue. So this was the problem with Flint, and we can get into it in more detail if anybody has a question about it. So, are there any questions?
Yes, again, go ahead and in the question box, viewers, type in any questions you have. This is a great opportunity, and then hit the send button. We do have some questions, Peter, so I'll go ahead and hit you with some of those now.
Good.
One question, what is the most economical way to eliminate lead from my drinking water? Some options sound more expensive than others.
Well, in my 40-plus years in the industry, I have to admit, in some areas regarding treatment technologies, I'm not completely objective. And one of those areas is on treating drinking water as a means of providing the comfort level to make sure that you and your children are drinking the safest water possible. And to do that, I am a very strong proponent of under-sink reverse osmosis systems. If you get one that's NSF listed, it will have activated carbon in it in conjunction with the reverse osmosis membrane. And these two technologies, in my opinion, do absolutely the best job of reducing. You can't eliminate 100% of any contaminant, but it can significantly reduce the concentration of both ionic or salts contamination, such as lead and arsenic and mercury, etc., as well as organic compounds. We have what I consider to be an ongoing potential issue in the future, particularly with surface water supplies, but also groundwater, with personal care and pharmaceutical product contamination, which are in virtually all water supplies at extremely low concentrations. But I'm convinced that ultimately the scientists will determine there is a health effect from these tiny concentrations of as many as 10,000 chemicals in our drinking water. And whereas it won't provide 100% assurance, the reverse osmosis system with a combination of activated carbon and the membrane, in my opinion, will reduce these concentrations by 70 to 80%. So having said all that, I think, in my opinion, reverse osmosis is far and away the best technology to use in an individual home.
Okay, we have a related question. The question is, doesn't RO, reverse osmosis, make the water more aggressive?
Good question, and I've had that asked to me on many, many occasions. And The short answer is no. And the reason why is because, let me use an example. If you have a typical water analysis, if you want to say there is a typical one, a typical total dissolved solids concentration of, let's say, 300 milligrams per liter in the water. That's all of the ionic constituents together would total about 300 milligrams per liter. These undersink reverse osmosis units at the most reject about 95% of the salts. So they permeate. 5% of the salts in this feed water would go through the membrane and end up in the drinking water that permeate. If you have 95% rejection of a total dissolved solids concentration of 300, that means that the permeate would have a total dissolved solids concentration of about 15 parts per million. You can go to Vancouver, BC, and the average city water there is 10 parts per million. My point being that when you're in that range of total dissolved solids, the water is not aggressive. Having said that, if I were putting in an undersink RO unit in my house, and you can imagine I've got quite a few in various places, if I were doing that and I were hooking the RO system up to my water in the door refrigerator or ice maker, and where almost invariably you have to run a line from the storage tank of the little RO 2.5 or 3 gallon storage tank holding the permeate. If you were to run that, usually you have to run it under the floor or across the room to get to the refrigerator. I would replace any existing copper piping that's used for that with polyethylene, with the standard RO pipe, just to ensure that there's no chance of anything dissolving. But I think a good rule of thumb is if the water total dissolved solids is above 10 parts per million, it's not going to be very aggressive. So it's a matter of degree. And so my short answer to this is that typically reverse osmosis treated drinking water is not too aggressive.
Okay, thanks, Peter. We have another question, and this is a question, by the way, I've gotten in the past from a lot of well owners here at the National Groundwater Association. The question is, what is the difference between a certified drinking water testing lab and one that isn't certified?
A good question, and I'm not sure I can answer it completely, but I know that virtually all labs, particularly those labs that are used by the state or the local government, invariably are certified. And I believe, if I recall rightly, that this certification involves meeting EPA standards. So, in my opinion, most of the labs of any consequence in terms of size are EPA certified, but that's an easy question that can be asked to this laboratory. What is your certification? What are you certified? Who certified you, and what are you certified to do? I'm not quite sure. It could be that an air quality lab would be certified only to test air, soil likewise. It could be that you can get certification for all three areas. I'm not quite sure, but certification is a very common requirement, and all it does is it's just like certifying the performance standards of the equipment that is being used. It means that it has been evaluated against specific performance standards and it meets those requirements.
Right. Thank you. We have a question about tap-mounted carbon filters. Do tap-mounted carbon filters remove lead? I seem to remember hearing that somewhere.
That's a good question, and unfortunately some of the media has indicated that in Flint these were carbon filters that were, they did qualify that by saying they met NSF drinking water standards. There is a standard by NSF called Standard 53, which is designed to qualify a device to filter out a health-related contaminant. Now, normally activated carbon will not effectively remove an ionic contaminant. And as I said earlier, that's the form that's dangerous with lead, in the ionic form. However, what many of these carbon filters do is they put a resin in with the carbon that will adsorb, it will remove this heavy metal contaminant. And they can be certified according to NSF 53 by a laboratory or by the National Sanitation Foundation. But it's not the carbon that's removing the lead. Now you could argue that that a carbon block could remove the particulate lead, yes, but the big concern is the ionic lead, this would have to have this addition. It's actually an ion exchange resin that's put in there. My whole concern about this, from a practical standpoint, is somebody gets this installed in their house in Flint, Michigan, and they leave it in and think it's going to last forever. And it isn't. It has to be monitored because there's a relatively small concentration of this ion exchange resin in with the carbon. And once it has adsorbed as much of the lead as it possibly can, and keep in mind the lead is very, very low in concentration. Once that happens, then it won't absorb it anymore. So it has to be monitored. Now, having said that, reverse osmosis doesn't work forever either. But generally, my experience has been, in all of the years, and I've probably installed well over 200 of these under sink units in friends and relatives' houses. I don't sell them, but I consult on them. I think, based on my experience, the average life of an RO membrane is 10 years because reverse osmosis doesn't adsorb it, it rejects it. It creates two streams, and the stream containing the bulk of the contamination is going to go down the drain. So that's a long answer to a short question, I'm afraid.
Correct me if I'm wrong, Peter, but I believe that a homeowner could go to the NSF website and can look up products certified for treating lead or other contaminants, and so it would be a way that the consumer could, before they go and purchase something, find some products that are certified to do what they purport to do.
Absolutely, and if I recall rightly, you may know this better than me, Cliff, but I think the website is at www.nsf.org.
Yeah, I believe that's true, yes. Okay, got another question. Says, when I get water tested at a lab, should I test the pH level first or the water coming from the tap to see if it has lead in it?
In my opinion, what you should do, particularly if you're doing the right thing, and that is checking the water at the tap, let the water run for about 30 seconds, collect about a pint of water in a glass jar, take it to the lab, and tell them what you want tested, and they will automatically test pH. That's one of the first things they test. You could, if you had the equipment, you could test the pH at the tap by yourself. There are test kits that will do that. However, that isn't going to answer your question, and that is, do I have any lead in the water? So what a lab will do is ask you what's important, what's bothering you as far as wanting to know about what's in your water, and then they'll run a suite of, typically a suite of tests. They'll test pH, they'll test total dissolved solids, they may test total suspended solids. There's a number of them, and a good lab will work with the homeowner and say, okay, let me tell you about each one of these tests and what they will do. They're not that expensive. but I would assume that if someone was concerned about lead in their drinking water at the tap, probably should be prepared to spend $70 to $100 to get a complete analysis. And to me, I think that's absolutely essential to have that done.
Okay, thanks. The next question is related, and it says, who takes the water sample for testing, me or the lab? How do you take a sample for lead? I think you've answered most of that, but maybe you can address just the idea that, or the fact that how a sample is taken can vary depending on what is being tested for.
Yes. A good lab, and let's say that you're really concerned about everything in the water, including organics, etc. The best way to approach it then is to contact the laboratory, tell them what is important to you to test, and in many cases they will send you the bottles, because if you're testing for certain metals, the bottle is going to have a little bit of nitric acid in it, just a few drops, to keep the metals in ionic form and stuff. For general testing, that it may not be that critical, but if you really are concerned, particularly as I said about organics and microorganisms, it's a whole complete different issue, because there it's absolutely essential that the water be kept cold. So you have to put it in a cooler with ice in it. It has to be maintained at 4 degrees Celsius. So when it comes to microorganisms, you just don't fill up a bottle and put it in the back of your car and take it to the lab. So to do it right, I would call a selected laboratory that has met your qualifications with regard to certification and stuff, and go through that. And they should be extremely helpful in giving you suggestions on what to use, how to collect the sample. If you're concerned, as we said in the webinar, about the lead leaching into the water when the water is sitting stagnant, then that might require 2 tests. The first test be immediately after sitting overnight. When you turn on the faucet, you collect a sample. And then after letting it run for a while, or in the middle of the day or something like that, collect another sample.
Okay, thank you. We have a question here. I don't know when exactly the plumbing in my house was installed, or when the well was installed. Should I be concerned?
Yes, in my opinion, yes. I think, in my opinion, the hazardous nature of this element is so great, and the chance of exposure is so great in terms of the various plumbing fixtures and the time in which they may have been installed. I think it's worth, as it said in the webinar, at least 1 test initially. In my opinion, I would like to see the authorities require, just like they do typically for nitrate and fecal coliform, or E. coli, I would like to see this as a requirement whenever a house changes hands, whenever it's sold or something. But I don't think that we should ignore the potential. We have, as a society, tended to ignore lead in our drinking water for years, but particularly if they're small children, I think it's a pretty serious issue, and so I would, just to be safe, I would have it tested.
Thank you. By the way, there's still plenty of time to take questions, so please type in your questions if you have them. We have another one here. Is there a way I can visually tell whether my house plumbing or well contained parts containing lead? So I guess they're asking if they can do their own visual inspection that would help them.
The answer is no. You can't. Because number one, lead is dangerous at such a tiny concentration, and number two, it's colorless, odorless, and tasteless in water. So you can't observe it. You have to have it tested by a laboratory. I know at one time there were some arsenic test kits that you could do in your home. To my knowledge, there are no lead home test kits. If there were, I would still say don't take the chance. It's not worth it. Spend the money and maybe once in your lifetime to have it tested. Because keep in mind, unless you rebuild your house, more than likely the problem is in the well or in the piping, either to the house or in the house. And so if you don't change any of that, you really should get by assuming that there is no lead. You have it tested once and that's it.
Okay, thank you. Another question, what are some of the pros and cons with different types of water treatment systems you mentioned?
Well, the three technologies that I mentioned, of course, number one, reverse osmosis, and I could go on to the rest of the day about that, but distillers, and they do an excellent job. The problem with distillers is that because what you're doing is evaporating almost 100% of the water sample that you want to use to drink, you leave behind a sludge, so they require constant cleaning of the boiling chamber. Number two, when the water first condenses, what you do with distillation is you evaporate the water and then you condense the vapor, and that's your drinking water, that's your treated water. That's typically warm, and we as Americans like cold water. You could certainly collect it and then put it in a refrigerator. Many people do. There is a slight problem with distillation, although I will say distillation produces a higher quality of water, slightly higher than reverse osmosis. But reverse osmosis will remove 99.5% of the lead, so it's also very effective. But the problem with distillation is that some volatile hydrocarbons that may be in the water, and by rights they shouldn't be, but they could be, anything that evaporates below the boiling temperature of water could end up in your drinking water, in your condensate. Some distillers have a carbon filter built in that may take it out, but generally, years ago when I first got in the industry, distillers were very commonly used as home treatment devices, but they just have tended to lose market share to reverse osmosis because of the low cost of RO and the fact that it requires little or no maintenance over a long period of time. The last technology, which is ion exchange, would be a special resin, not unlike that's used in a softener, but this is a resin that would be used under the sink, typically. The problem with those is they adsorb, they take out the contaminant and they keep it in the resin. They don't throw it away like RO does. So they don't have two streams, one good quality and one poor quality like RO does. But having said that, they adsorb all of the whatever you're trying to take out, and so eventually they have to either be replaced or regenerated. Again, they require more maintenance than RO, and because of the fact that a DIY store sells these RO units for as inexpensively as $180, $190, and you can install them yourself, and they're as good as anything on the market. They're NSF listed. So in my opinion, that's why I'm such a proponent of RO, but these other two technologies will also work.
Okay, we have a question. Do those acid neutralizing systems change the taste of the water? I guess maybe we could expand that to do any of these systems change the taste of the water, and how? So I guess we're having a question about the aesthetic quality of the water after treatment.
Well, I'll first address the pH adjustment. There are two kinds of materials that are used to raise the pH of water. One is calcium carbonate. That's what a calcite filter is. It's granular limestone. And what happens is this water will go through the limestone. It'll tend to dissolve some of the limestone, which automatically raises the pH. This is the most common method that is used in seawater desalting systems to make the water more potable. The taste of water is extremely subjective, but generally an acidic water is not very tasty. That's the normal reaction of people. Putting a little bit of calcium carbonate in it improves the taste to most people. Interestingly enough, temperature has a huge effect on taste too. But the other pH adjustment resin is called Corrosive, and it's magnesium oxide. That will also impart quote, more pleasant taste. There are people that with regard to the other treatment technologies, something like the ion exchange resin should have little or no effect on the taste, because nothing is put into the water like it is with the with pH adjustment resin. Distillers are claimed, distilled water is claimed to not be as potable, and that's probably because distillers remove the dissolved oxygen. Dissolved oxygen seems to make water more potable, more tasty. Reverse osmosis does not remove the oxygen. So most people that taste RO water think it tastes great. If their drinking water has something in it that has affected their taste, like chlorine, for example, they feel that RO is fantastic in terms of taste. RO will remove the total dissolved solids. For example, if you live in San Diego, where the drinking water, tap water, is relatively high in dissolved solids, people may get used to that salty taste contributed mainly by sodium chloride. And so they get into a different drinking water supply, even if it's RO, and it tastes different. But most people in general seem to prefer the taste of RO water to the other choices. But like I said, it's a very subjective issue.
Okay, thank you. We have a real specific question here. The writer says, I want to sell my house in Pennsylvania. Built in 1958 or 1959. It has a private well. Lead test was conducted by Penn State lab 3 months ago. No finding of high lead level in the water. From a water standpoint, do you recommend I hook up to public water to make the house more sellable?
This is just my own opinion, but I'd say absolutely not. I think if you've had your water tested and it meets the drinking water standards, go for it. That's not saying that your well water, depending on the depth of the well, et cetera, could not eventually change. But tap water, city water, often changes depending on the source, and it's more likely to have these PPCPs, this personal care and pharmaceutical products in it. If I were in your position, I would, and if you're happy with the way the well is working, the quantity, etc., I would say stay with the well.
All right, thank you. We have one more question which I can answer, and that is, can you post the presentation as you usually do? I'll go ahead and answer that. Yes, we are going to make that presentation viewable via a link, and so we will be sending that link out to everyone who registered soon after the webinar. And I would encourage you to go to our National Groundwater Association website called wellowner.org, wellowner.org, to find other webinars that we've done and some online lessons on the same topics accessible to you at any time you want to view them. So I will, with that, oh, and then one more thing. Nope, no, I already said it. I was going to announce that before somebody asked it. So with that, I'm going to go ahead and turn it back over to Peter to close us out.
Okay, as Cliff said, here's the website for well owner location at National Groundwater. And as he said, you will have access to this, so you don't have to rigorously write any of this information down. This is a list of questions that you can get answered from wellowner.org. And then my phone number and actually my email address, and it's on my website, which is listed here, but my email address is P as in Peter, S as in Sam, Cartwright @msn.com. Either one of these, I might point out the website is wrong. I just noticed that. It's Cartwright sub, what do you call that? It's not a dash, it's a
Underscore.
Underscore, yes. Cartwright _ consulting.com. But the phone number is right. And although I'm an independent consultant and I do not sell anything tangible, I do encourage anybody that listens to me, if you so desire, send me an email or give me a phone call, and if I can answer it with little or no expenditure of time on my part, I don't charge for it. I think it's very important that we all understand as much as we can about this very complicated subject of water and water treatment. And so I encourage you to contact me at any time. And NGWA can also put you in touch with me if you're unable to do that from this information. So thank you very much for attending this, and like I say, feel free to contact me if you need some more questions answered.
Yes, I want to thank everyone as well, and please go to wellowner.org to look for upcoming webinars on other topics related to private wells. Thank you very much, and this concludes the webinar. Thank you.